Hello, everyone, and welcome to the Learning Curve, Scale AI's Tech Talk series. Today's topic is on the game theory of human-in-the-loop labeling, and our presenter is Akshat Bobna. For those of you who are not familiar with Akshat, Akshat is an engineering manager at Scale, where he leads a team that's building the software and systems to label text, audio, and computer vision data for machine learning teams. Before I hand things over to Akshat, a quick housekeeping note. If you have any questions as we go along, please submit them using the Q&A feature, and we'll address them at the end of the presentation. Thank you. And with that, Akshat, take it away.
Thanks, Yuri. Right, set this up. All right. Yeah, so as you guys have heard, the topic of my talk is humans in the loop don't perform gradient descent. And this is basically a synthesis of like a lot of things we've learned over the last years from labeling literally billions of frames of computer vision and text data. And my goal today is to present a few of those insights that really show why data labeling is such a hard problem. In particular, I'm going to focus on the incentives aspect of it because this is something that we've seen is curiously lacking in the research. And perhaps it's because there are not a lot of human-in-the-loop systems today that operate at the same scale and complexity as us. So for today's agenda, I'm going to first introduce Scale and provide some context on what we do, and then also introduce the problem of human-in-the-loop labeling in general and what's hard about it. Based on that, I'm going to introduce a model of quality incentives that can be used to structure our thinking around this. And using that, we're going to build a model of, we're actually going to build a system that allows the production of high quality labels. And what are the challenges that happen with that? And I'm going to leave time for questions at the end. And I think you can ask questions through Zoom. There's a feature in the webinar for that. Great. So some context. What is Scale AI? What do we do? Our mission is to accelerate the development of AI applications. We were founded in 2016 by Alexander Wang. We're about 250 strong at the moment, and we're growing rapidly. And the central thesis of Scale is that there's a sort of paradigm shift from traditional development of applications to development of AI applications, which is, whereas the original step used to be for production, you had to write code and then you iterated on it. The shift now is that you actually have to gather a lot of really high quality labeled data, and improvements in your applications happen by getting more and more labeled data and being able to iterate on it. And we also know that currently in areas such as perception and NLP, humans are still the main way to generate ground truth data sets. So to enable ML teams to make faster progress, we began with making data annotation products. Today we have a whole suite of them, from perception to NLP use cases. In some use cases that we're really focused on today are on the perception side, we work a lot with AV teams, robotics, AR, VR, and on NLP, we've been working on document transcription, question answering, classification, and search relevance. We also recently launched our first data curation product called Scale Nucleus, which allows ML engineers to understand and really dig into the data they have. And over time, we've had the privilege of partnering with some really incredible customers. In particular, some to call out are AI, Airbnb, Pinterest, a whole host of self-driving car teams, and so on. And really quickly, what is sort of how does a data labeling pipeline look like? So this is a very simplified version of a data labeling pipeline Scale, where we get a customer census data through our API. It goes through our automation engine, which is could be ML pre-labeling, it could be other pre-processing of various forms. And then it goes through a whole series of humans that label it, process it in various ways before it gets to a customer. And this is basically what human in the loop means. It's humans interacting with models to produce an output. In addition, the way this works at scale is that it is a two-sided marketplace, which means that we have customers that want data labeled, and we have taskers that want to label data, and we match the two. This sounds kind of simple. It sounds similar to a lot of other marketplaces you might have heard of. And I'm actually going to use the marketplace example, using an example of another marketplace that you would already be familiar with to illustrate why it's actually a lot harder. Yeah, so let's actually talk about ride sharing, which I'm sure at this point almost everyone attending has used and experienced. And in particular, I'm going to talk about three pillars of that you have to worry about when you build a marketplace like this, which are training, which is for the side of the marketplace that's providing the service. How do you give them sufficient training and make sure people on that side are capable of performing that? I'm also going to talk about tooling, which is how do you actually enable them to perform that service effectively by giving them software, hardware, and so on. And finally, quality assurance and incentives. It's the marketplace's job to make sure that the service provided is of good quality, and also that people are paid fairly for the work that's done. Great. And in the ride-sharing example, how does training happen? Well, a lot of it's actually taken care of by the DMV. You don't actually have to teach someone how to drive a car from scratch. They come in with that knowledge, and you can check their driver's license for certification. There is some basic amount of onboarding in the app that teaches them how to interact with it, what to do and not to do, etc. In terms of tooling, whether you're delivering groceries or picking up food at a restaurant or driving people from place to place, it is pretty much the same interface. And it's pretty low skill cap to learn. And finally, QA is actually super easy because the customer gives you feedback on every ride. And also, payment is proportional to effort. So you know how long someone drove for, what is the distance they covered, and you can build a pay formula around that, maybe with some modifiers for demand, bonuses, things like that. Obviously, these things are more complicated than that, but the point here is that you can conceptualize what this incentive structure would look like. Great. Now let's get to data labeling, and I'm going to start off with a really simple example, which is what if we're classifying cats and dogs? And training here is implicit. We all know what cats are, what dogs are. Tooling, I don't need to say much more. And for quality assurance, we probably would get good quality right off the bat, but we really want to be sure we can have consensus of 3 people to make sure that the quality is good. And we can also pay people for a task. Maybe we can have a bonus for accuracy, but all of that also is really straightforward. Unfortunately, that's not the reality of how easy labeling is today. And to illustrate that, I'm going to talk about LIDAR segmentation, which is one of the task types that we offer today. And some context on what LIDAR segmentation is that it's like 2D panoptic segmentation, except for point clouds. So for a whole 3D scene or a point cloud, you have to label every pixel and tell us what it is. So it's kind of like painting in 3D. So when you get to tasks like that, how do you train people? Well, the challenge is that there are like almost 50 categories of objects in some of these tasks that someone has to learn and has to be trained on how to label. They have to learn a lot of decision trees of what to do in specific situations. Like what do they do when there's a parking lot or there's a beach or it's a nighttime scene and so on. And obviously, a lot of these things come with a really long tail of edge cases, like how do you segment a car that's being carried on a truck? Or is a skateboarder a pedestrian? Questions like that, which are really philosophical in nature and hard to answer or have a definite answer for. Right, and in terms of tooling, we actually have to build our own 3D graphics. We have to worry about how to render them efficiently. Here's an example. We have to build sophisticated navigation controls and of course teach people how to use them. And we also build a lot of ML-assisted smart tooling. Like we have a magic wand tool that helps people be really fast during this kind of labeling. And finally, how do we think about quality and incentives on tasks like this? Well, the problem is that you can actually have a lot of correct answers on a task that's so complex. Like you can imagine there are a lot of different ways to segment an image that are all correct. And it also takes a really long time to audit one of these tasks. And let's say if you have figured out the quality, even then pay is a further level on that because you cannot actually pay people the same amount per task or even considering accuracy in some sense, because there's a lot of variance in how complex each task is, even within a project. To understand why that is, we could have someone who's driving through like a highway at night and there are no other cars, and that's really easy to label. Or they could be driving through Chinatown in the middle of the day, and then this is a real example, by the way, there's hundreds of pedestrians that you have to individually label. So that makes pay really complicated and something we have to think about. So our focus for today is this quality and incentive system. And that's because I feel like design for the quality and incentive part of labeling is not talked about often enough. And so we're trying to fix that. So what is the model of, sorry, I'm gonna let this siren pass. Sorry about that. Yeah, what is our quality and incentive model? So let's start off with something really simple. We have a data set and we want to predict labels for it and give them back to the customer, like so. And when we give them back to the customer actually has some true labels that they can, and their main metric is that they want the accuracy of labels they send back to be high, and they give that feedback to us. And of course, customers don't actually have access to this ground truth. So in practice, how this works is that for the labels we send back, they might sample a random portion of these and then give us feedback based on those. And so in this really simple case, Scale is sort of a broker between customers and testers, and we're just passing the work along front. Unfortunately, that doesn't work. You can imagine that, well, the one problem is that auditing tasks has a lot of latency. It has a lot of scalability issues, which means that in practice, we can have 10,000 people work on projects for a single customer. And so obviously we cannot audit all of them. We cannot audit all of them consistently. And QA from a customer is also its own can of worms. It kind of circularly goes back to some of the same problems we're trying to solve, but we're not gonna go there. Right, so what we can do is we can actually intermediate, and we can estimate the customer's accuracy for ourselves. So we have our own loss function based on the data set that's sent in and the labels predicted by the tasker. And based on that, we can give the taskers a reward to incentivize them to produce higher quality. So we've solved some of the issues. We've taken the burden off the customer, but we really haven't solved the problems with consistency and being able to scale up to a large amount of data. And to do that, we realized that the main problem is that we have a lot of unlabeled data, and the only way we can judge its quality is after it's labeled at the other end. But it doesn't have to be like that. We can actually modify the data set we're giving to the testers themselves. And for example, introduce tasks that we already know the answer to and so on, and then use that in our final accuracy metric to know accuracy with lower latency and have higher confidence in it, so on. So, oh, cool. Sorry about that. Noise. And I want to talk about why am I framing things in this way in this particular language. So what it's actually doing is it's making explicit what every party is optimizing for and where we can apply leverage. In particular, if you look at this, it's clear that taskers are optimizing for the reward they're getting on the particular badge. They're maximizing for that. And we're not only maximizing, we're not only minimizing the customer's loss now, but we also incur costs from increasing the size of this data set. And we're also minimizing the costs incurred from that. And right, basically, labeling at the end of the day is a problem of incentives. And we've found out over time that thinking about taskers' incentives is often the best way to influence throughput and quality. And so this model kind of makes that explicit. Also, like any other analogy between domains, it encourages us to use techniques and wisdom from one domain in different applications. So we can think about how can we use loss functions from ML to evaluate taskers? How can we best class balance our data set if we're giving taskers a whole batch of assignments? How can we be sample efficient in exploration when we're figuring out what taskers are good and bad at, etc. And of course, it's not the only framework for thinking about labeling. Some other popular ones are thinking about quality assurance in a manufacturing process. A lot of these problems have been solved before in industry manufacturing when you're trying to get a high quality product. How do you sample things efficiently? How do you make sure people are calibrated and so on? One other interesting one is item response theory or test theory, which allows you to think about how do you actually assess what different people in your system are good and bad at. Cool. And with that, I'm going to talk about how we can actually build the system. So the first thing is how can we actually modify taskers' assignments so we can have a more accurate accuracy metric at the end of the day when they've labeled those tasks. And what that means is that we give taskers a whole mix of assignments, and it's kind of like training, testing, and prediction at the same time. Like you want to give some, you want to mix all those things in partially for reasons of you don't want to make it clear to a tasker which things are testing them and which things are not. And you also want to have continuous retraining because unlike models, humans can regress or forget things or degrade in performance. Cool. So the main, well, it's not the main thing, but one thing we really focus on at Scale is thinking about benchmark tasks, which are basically tasks that we know the answer to, and we augment the data set we're giving a tasker with these benchmark tasks. And in particular, if you think about it, you realize that there are certain properties that benchmark tasks need to have. They have to be indistinguishable, which means that taskers should not be able to tell which tasks are benchmarks and which things are real tasks. Empirically, we validate that many number of times. Like for example, we had at one point when we had a brief bug where like the timer on the task was different for benchmark tasks and real tasks. People quickly converged to being able to figure out how to work in that system until we quickly fixed it. And so if anyone's skeptical of how adversarial data labeling can be, that's a good example. We also want benchmark tasks to be representative to illustrate if all of our benchmark tasks are really easy, then we don't actually get a good assessment of how tasks are doing on the actual tasks we're giving them, which are much harder. And of course, the benchmark tasks have to be really high accuracy. That kind of circularly goes back to the fact that you need high accuracy ground truth for data labeling. I have a question here. I'll get to questions at the end. But basically, it kind of goes back to how we need high accuracy data for data labeling. In a similar way, we need high accuracy benchmark tasks to train our taskers. And all of our decision making and all of the feedback we give them can only be as good as the benchmark tasks we're assessing them with. Great. Cool. So now that we have a sort of table stakes formulation of benchmark tasks, let's actually talk about some problems that happen when we try to run them in production. So one thing that comes up is that the data distribution actually evolves over time. And to illustrate, we worked on this project with OpenAI where we're classifying snippets from GPT-2 in an active learning fashion. What that means is that the model trains over time and it picks which data points it wants labeled. We label them, it gets better and sends us more data points. So and as it gets better, we actually saw that inter-rater agreement actually dropped over the course of the project, showing that tasks are getting harder, more ambiguous, and so on. However, the quality as measured by our benchmark tasks remained the same. It actually went up as people got better at the task, or the benchmarks at least. And so what this shows is that this is sort of a condensed example, but even for customers that are not doing active learning, their models are getting better. The kinds of data they're sending us do get harder week by week. And it really shows us that we need to be continuously curating our benchmark tasks, and we need to be continuously mining more. Also, if people have questions, you can also post them in the chat if there are any immediate clarifications I can provide as they go along. Cool. So another problem that happens is that we can have imbalanced classes in our benchmarks. One example I love to use is that birds make up 2% of annotations in a given project, but are actually really important to get right, because you can imagine for a self-driving car, if they don't know how to detect birds, then they're going to go crazy on the road. But if we just did this naively and we made our benchmarks from a random sample of tasks, then it's quite likely that most taskers would never even have been exposed to a task that has birds in it. Or even if they have, we don't have enough samples on the taskers themselves to know if they're good at labeling birds or not. So the solution to that is we actually need to put in a lot of effort to class balance our benchmarks. And not only that, we actually incur a big cost in every time we give someone a benchmark because they're not labeling real data, but they're labeling fake data. So we actually also need to work on being really sample efficient in serving these to our taskers and really understanding their strengths and weaknesses really quickly, making sure the benchmarks we're giving them are going to be high signal for the particular tasker themselves. Great. Another thing that can happen is we can have like benchmarks can bring up latent patterns that allow taskers to use heuristics. And I'm going to go back to the OpenAI example. So some more context is that the project we worked on, or one of the many projects we worked on with them, was on fine-tuning GPT-2 using human labels. And so the point of the task is there are snippets from GPT-2 and some possible continuations. And you have to pick the most descriptive continuation, or you have to pick the best summary as made by GPT-2, and so on. And something that our taskers converged to over time was they realized that the longest summary was often the best one for a task. And you can imagine why that is. And in fact, in our data set, or in the data set that OpenAI was giving us, it was actually the correct answer for like 80% of the tasks that we were labeling for them. So the way we got around that is we have a really robust benchmark task system that works based off of metadata that we attach to each benchmark. So it can use that to serve them more efficiently, to know what people are bad at or what categories of benchmarks people are good and bad at. And so we added the ability to tag them based on automatic rules. So in this case, you actually want to tag benchmark tasks where the shorter summary is correct with a special tag. And then our system can give them to people in a balanced way. It can make sure that they're actually good at that particular class of examples as well. And then finally, we very quickly eliminated this problem once we spotted it. Any questions so far? In the chat. Great. So benchmark tasks are not the only way we can augment the assignments we give to taskers. There are a bunch of other things we do and that I wouldn't go into today, but some of them are, we create synthetic tasks. We can actually also create synthetic annotations within a real task. We can add more structure to tasks, for example, decision trees. What this means is that even if a customer does not care about a particular thing at the end of the day, we might want taskers to provide those answers so we can be more effective at quality control and gather more metadata about the kinds of tasks we're labeling, things like that. We also break down a lot of problems and we formulate them before they end up with the tasker to decrease variance and present them in a way that really sets up taskers for success. An example of that is a lot of a really long, complex tasks. We instead of having all the taskers define all of the annotations, after the first step of labeling, we actually have them done on a per annotation basis. And that allows us to do all of the other quality control on a per annotation level and gives us that much more confidence in the quality of each annotation. Great. So now that we have that, how do we actually use these assignments once they're done to construct an accuracy metric? And what that brings us to is what actually is a good metric. So it actually needs to have a few different properties. It needs to be complete. That means that it has to have a term for everything the customer cares about or that we want high accuracy on. Again, this has been validated empirically a number of different ways. For example, we once had a project that had low accuracy, in particular on positions. And then we realized that it was because of a misconfiguration where we had 0 weight for position itself. Once we fixed that in our accuracy metric, the metric, since it informs reward to taskers and so on, accuracy on that thing went up. Obviously, you cannot just, not only do you need a term for everything, you also need to weight them correctly. That goes without saying. And finally, the metric has to be interpretable, not only for us to understand why quality on a certain project is a certain way, but also to be able to communicate feedback to taskers in a really actionable way. Great. And immediately, even then, you run into some challenges. The first challenge is instruction ambiguity. So the task on the right is another one from our OpenAI project. And here, someone has to pick the most descriptive continuation of the paragraph. I am actually going to give people a minute or so to read this task and example. And I was going to suggest people in chat can post what they think should be the most descriptive continuation. So I'll wait for that 30 seconds. Great, I'm getting a lot of B's and C's. I think people cannot see the entire chat. Yeah, I think I would agree with B, but as you can see, it gets really complex because even when you're answering a simple classification problem, you actually have to weigh a lot of different things in your head. Like, how do you weigh correct grammar versus correctness of content versus descriptiveness, which is what the task ostensibly is testing for, and so on. And it's not really, you could argue like you can solve some of that by making the instructions more specific and being very pedantic with them. But it's not really possible to do that without making the instructions really complex. And you still always have some edge cases. This is kind of why we have humans doing this labeling in the first place, because they can exercise judgment in areas that are ambiguous or underspecified. And what that means in the computer vision domain is, before I get to the challenge, here's another task. This one is we have to label drivable surface for self-driving car. And it turns out that both of these examples here are correct. And that's because the customer doesn't actually care if the polygon hugs the vehicle's underside or not, because they're not opinionated about that. But they do care if the left side goes onto the median, because that's obviously not a drivable surface. And what that ends up being is that we cannot just optimize IOU, right? Like we cannot, if someone submitted this answer and we thought this is ground truth, IOU for that wouldn't be great, but actually would be correct. Whereas even a small deviation here would have high IOU, but would actually not be correct. And so to summarize, what's happening is that we have a lot of ambiguity instructions that makes multiple possible responses correct, but not systematically. And also, the batch of data that every tasker is labeling is really small compared to an ML model where the model gets a huge batch of data, a lot of things are averaged out, a lot of noise is averaged out. We actually have very low noise tolerance because we have to infer if people are correct or not from just a small batch of data. And finally, I want to talk about reward, which now that we understand how we're giving tasks to people and how we're estimating their accuracy, is the most important piece, which is how do we actually give them feedback and pay so that they're incentivized to produce high quality data. And before we talk about it, the most important thing to call out is that taskers are not optimizing for the reward or itself, but they're optimizing for reward over W here, which I'm calling the amount of effort or time taken. This is really crucial. What this means is that even if someone gets paid more on a given task to go from 95% accuracy to 99% accuracy, if it takes twice the amount of time to them for doing the task, they're not going to want to do that unless they also get paid twice that amount, right? And this is another key difference from training an ML model and why we cannot just use a loss function from ML for taskers, because you can just ask a model to care about a reward and optimize it, whereas a tasker is actually optimizing reward over the effort that they put in. Cool. So to rephrase that, what that means is that reward over effort should be monotonic in accuracy. and higher accuracy should mean higher salary. We have a lot of evidence of that. Here's another example. This to prove a point, which is we had a project where incentives are misaligned. So the graph over here shows the quartiles of accuracy and how much they're getting paid. And there was an inversion where the top accuracy quartile was actually not making much amount of money. And so accuracy in the project was low. When we fixed the incentive misalignment, accuracy went way up, as you'd expect. Cool. Another interesting thing is that reward cannot simply be a function of time spent on the task. And the reason for that is that we cannot actually open our, like, that opens malicious people to game the system in a lot of different ways. And but we still need a way to actually know the inherent complexity or the inherent difficulty of various tasks. Like I have a really pathological example here of a task that had literally hundreds of cuboids because the car was going through a parking lot. And so obviously you want to pay people proportional to the amount of effort they're putting in. And the solution for that is we actually independently model the work based on variables like number of annotations, sometimes even metadata like time of day, and use it to calculate the reward. Great. Another challenge is that the value function for the customer is actually not proportional to the amount of effort a tasker has to put in. What that means is that we might want to weight some underrepresented classes or some really hard or egregious classes really highly, which would mean that the weight for really common classes is relatively lower. But it could also be that some common classes, like in this case, I've picked segmentation, such as vehicles. In this case, I've picked a 2D segmentation task where vegetation is a really common class and needs a lot of effort to be labeled correctly. You have to get all the details and the leaves right, like over here. And so you actually also want to consider in your weighting how much work it takes to do different classes. And so what we realized is that there are actually two different sets of weights. There's the sets of weights for the accuracy itself, which is what the customer cares about. And then there are also a set of weights that tell us, as we talked about before, how complex different classes are, so we can actually understand the total amount of work in a given task. Great. To add more complications into the mix, we actually allow taskers in our system to reject tasks, which means that taskers that are operating, that are really trusted, are actually reviewing other people's work. And since we don't want them to be fixing a task if let's say it was left completely undone, they should have the option of rejecting it and having it go through our pipeline again. However, that makes thinking about incentives and people's strategies here a lot more complex, because something we have seen before is when you have an infinite supply of tasks, you can actually end up with people cherry picking tasks that are almost complete, because why would you go through the effort of fixing if you can find one that's already almost complete and send that through? So that also means that we really have to think about incentives and make sure that people are incentivized to fix, as well as to fix, reject, and accept in the right situations. Great. And there are a lot of things that I haven't talked about, such as how do you model the confidence in various taskers? How do you attribute work when a lot of people work on a complex task? How do you actually propagate trust scores from taskers at a higher level or higher trust to taskers at a lower level? How do we construct ML-based and automated quality signals? And finally, the graphic here shows how we can surface edge cases from a customer and actually discover their metric or their loss function. Great. And throughout this talk, I've talked about taskers really abstractly, I want you all to know that that's not how we think about them at scale. We know that the work we're doing has a really big impact on people's lives, and so we truly understand the weight of what that responsibility is, and are always in dialogue with their taskers to understand what their real pains are, what they like, what they don't like about our platform. If anyone's curious in understanding what the life of a data labeler looks like, we actually have a blog post on that, which I encourage everyone to read on our website. And that's it. We have 15 minutes left. I'm happy to. We have a Q&A section that I cannot actually open. Uh,
Uh, Thanks for that, Akshat. I'll read you some of the questions in the Q&A here. So first, it would be great if you could explain why using a different task should help the actual task. So suppose our task is something very niche, say labeling pests on plants where labeled data sets don't exist already. So how would we be confident about the labels here?
Got it. Yes, I think I understand the question, which is maybe what you're getting at is like, are we using different tasks that are not the task itself for checking people's work? And actually, it's not the case. Something I talked about in the presentation was we want our benchmark tasks to be representative of the real task. So that allows them to be indistinguishable, and so we can actually understand people's performance in the real case. And so in your case, even if the task is really niche, that is something that is part of Scale secret sauce, which is that we can actually, we have a lot of work on how to construct benchmark tasks for all of our projects. In a lot of projects, we do that in an automated way, which is, you can imagine a process where when we get a batch of data from our customer, we actually take a small portion of it and we have it labeled by a really trusted workforce, or we have it labeled like 10 times over. And then we can really understand the properties of that project before we use those tasks that we just labeled to then check the quality of the rest of the workforce. Does that make sense? Happy to elaborate.
Thanks, Akshat. Right. Second question here, how do you handle cases when there is no major consensus on a label?
Yeah, that's a really good question. So we don't use consensus on all of our projects, but once we do, it is possible that some tasks are really hard and people disagree on what the correct answer is. In a lot of cases, what we do is we then escalate it to someone we have a lot more trust in, who is somewhat of an expert in that task, and then they have the final authority to adjudicate what the label there is.
Great. Third question here is, how do you deal with instruction ambiguity?
Yeah, that's a good question. That's something I talked about why instruction ambiguity is a problem in the slides. What I didn't talk about is how we actually solve for it. And there are a few different, there are a combination of things we do to solve it. One thing is we do make decision trees more explicit in a lot of cases, so we have an understanding of what taskers are doing, what they're not doing, and try to structure our instructions so that it's easy for a human to follow a flowchart in a lot of cases. In a lot of other cases, we actually, for a benchmark tasks, we don't actually have one correct answer, but we curate a set of correct answers to understand like the distribution of how people who are good actually label this task. And then we can grade against a distribution that that gets around a lot of these problems of having multiple correct answers.
Great. At what point is it worth splitting up a task?
Yeah. So this is something that we're still trying to fully understand and really experimenting with. But we do know that beyond a certain point of having a lot of categories to label or a lot of instructions to understand, it places really high cognitive load on taskers, and people are just not able to reach really high levels of accuracy on those tasks. At that point, we can split tasks up into either having different people do different labels, or split up different uh, things you have to do in the task. Like, for example, the box drawing responsibilities could be different from the person who's actually filling out the attributes of each box, such as is it parked or is it occluded, things like that. Yeah, it's still something we're trying to understand, but it's definitely a real effect.
Great. And what if labelers have a clear majority on the wrong label?
Yes, that's a good question. So that's basically where our ground truth or benchmark tasks come in, which is not only are people is their quality being measured in one way, which is how much they agree with other labelers, but we're also measuring how like their accuracy against a golden data set that we're pretty confident in the answers of. So if they are if labelers are misaligned with that, then they're given feedback or filtered out. And that makes sure that people who, even before they go into consensus, they have some like baseline level of accuracy, which makes it really hard for everyone to actually reach a majority on the wrong label, if that makes sense.
Great. And do taskers actually optimize for pay per hour? What are the other factors they optimize for?
Yeah, so it is, of course, somewhat of a, like we're making a simplification by saying people are just optimizing for pay per hour. Although we do know that over time people converge to certain behaviors. It's also not that surprising that it happens, because there's a lot of information sharing, and in fact we also really want our system to be transparent, so we give people a lot of feedback on why their pay was a certain way. So they actually have an incentive to try and optimize it, try and like figure out what they can do to get higher pay, because our thesis is that if we make sure that people know that higher pay is aligned with better accuracy, then everyone wins. But given that, there are also other things people care about, like the latency of pay or the consistency, overall task to experience. We actually also really think about how to build a community of taskers. It's kind of funny, but some of our taskers are it's really sweet that people have actually found friends while labeling on our platforms. I really enjoy.
Great. Can taskers be banned?
Um, yes, I mean, as with any other website or system that deals with fraudulent activity and has to worry about spam, we do like in the cases of really egregious behavior, like trying to defraud us in various kinds of ways, we can ban taskers.
Thank you, Akshat. I think that's all the questions in the Q&A. I would like to do a last call for questions if anybody has any. Great. One more question here. Are taskers all English speakers?
Yeah, that's a really good question. They're in fact not. We, especially for NLP efforts, we support labeling in multiple languages, and So we have taskers who speak French, Spanish, and various other languages. Yeah.
Is there a heuristic for how many taskers a task is served to?
Yeah, that's a really good question. There's really it's it's not that there's one heuristic. This really depends on the nature of every task we're doing. In particular, what we're trying to get at the end of the day is like how many people should this task go through, such that after going through a pipeline, we think it's high accuracy. A lot of it is actually dynamic, where based on like after someone works on a task, then based on certain signals, um, like how they interacted with it, what are the particular skills of that person, are they really good at labeling bikes or something? Like all those things actually feed into determining if that task is needs another pair of eyes or if it can be sent out.
Great. We'll give, I guess, one more minute here for any other last minute questions. All right, doesn't seem like we're getting any more. So with that, thank you everybody again for attending. Thank you, Akshat, for the insights. For everybody who joined, a recording will be made available and sent to your email either later today or next week. So thank you again for joining, and we hope you join us for our next round of Tech Talks. Thanks very much.